Hi everyone, welcome back. In this video we're going to do a DC analysis of another common emitter transistor amplifier, but this time the biasing is using what we call a potential divider biasing. So if you see the potential divider here, that's between R1 and R2. That's what's being used to bias the base voltage. All right, so let's begin. Well, first of all, obviously we need to label all our currents and voltages so that we understand what is positive, in which way is it positive, and so on. All right. Okay. So first of all, let's just do this. This is the collector current. So collector current is positive that way. Base current is positive that way, and emitter current is going to be positive that way. And then for our voltages, we have VCE, that is positive that way because current is flowing downwards. So same with RC, it's going to be positive that way because IC is flowing down, so positive RC would be going up. And similarly for RE, since IE is coming down, so the positive voltage of RE would be pointing up. Now I'm not labeling the left side because we need to convert the left side into a Thevenin equivalent. All right, so Thevenin equivalent circuit. All right, so a Thevenin equivalent circuit is a circuit that replaces these three components with a single voltage source and a single resistance. All right, so for those of you who needs a bit of refreshing, so basically I have a sketch here. So this is how our Thevenin equivalent circuit is going to look like. All right, so it has a single VTH and a single RTH. Now I've kept the node labeling as per original. So you have the node at the base at is 1, and the node below RE is 0. So that is still the case. So that you understand that this is a plug-in replacement for this side of the circuit. All right. So that would include V1 as well, but remember that V1 is actually connected to both R1 and RC, so you can't remove that entirely. All right. So first of all, let's work out the VTH and RTH. So Thevenin equivalent. The calculation would be for VTH is going to be equal to basically it's a potential divider. So it's going to be V1 into what's across R2. So basically it's just R2 divided by R1 plus R2. All right, so it's just a potential divider. All right, so that's our VTH. All right, let's just work it out straight away. So you know that V1 is 18 volts, all right, 18 volts, and then R2 over R2 plus R1 is simply 8K, is simply 8 divided by 8 plus 56, all right, so that's going to equal to 2.25 volts, all right, and similarly for RTH. So RTH is, if you guys remember from your Thevenin, basically we zero the source, and once we do that, the top part of R1 will end up at the bottom, and therefore it will make R1 and R2 parallel to each other. So R1 is going to be parallel to R2. So that's going to equal to 7 kilo. All right, let's just bring that down a bit. Okay, hang on. All right, so let me bring this down a bit so you can see. There, 7 kilo. All right. Okay. So now we have our RTH and VTH. We can actually redraw this circuit so that we can then work out a new kind of loop. So the circuit would then look like something like this. All right. So you still have the Thevenin equivalent here. All right. So node 1, node 0, that's still there. Now imagine I just plug that into our original circuit. So the right-hand side will still remain. So this is the right-hand side, plus even the V1 of 18 volts that's connected to on top of RC. So that all that is still there. All right. So and all the directions remain unchanged. All right. So let me maybe highlight that a bit. So we have VTH that is pointing up. We have RTH that is positive this way. VBE that is positive that way. And then you have VRE that is positive that way. All right. So you have IB that is going in. All right. So this is still IB. All right. So IB is still going in like that, and IE is still coming down like this. Okay. So might as well just complete the rest. So this is of course IC, and the voltage across RC is positive going up. VCE is positive going up, and VRE is already there, so V1 is also positive that way. All right. So we can now write equations about our small loop over there. All right. So let me just write that. So left loop equation. All right. So we're just applying KVL. So we're going to get VTH is equal to VRTH plus VBE plus VRE, right? Okay, so we can actually we can. Okay, so then now what we do is we're going to convert, because we know the VRTH, that's the voltage across here. You can write using Ohm's law as IB times RTH, right? And then VRE, this voltage here, again we can write using Ohm's law. It is IE times RE. All right. So if you do that, you're gonna see. Well, okay, let's just write that out so you see what I'm talking about. So this is going to be VRTH is going to be IB times RTH. All right, plus VBE, which we will assume to be 0.7 for silicon transistor, and VRE is going to be IE times RE. All right. All right. So we have two unknowns, IB and IE. So what we can do is, well, we have these two sets of relations, so we can actually do something about it. So if you look at IE, well, IE is equal to IC plus IB. But then we can replace IC with IB times beta. So then IE can be written completely in terms of IB, right? So let me just maybe put that as a reminder. Note that. All right, note that. IE is equal to IE is equal to IC plus IB. All right, and that is going to be equal to IB times beta plus IB, which is going to be equal to, if I were to factor it out, IB, and then it's going to be beta plus 1, right? So IE is just simply IB and then beta plus 1. So then we can, well, obviously, substitute all that into our equations here. So VTH, sorry. So VTH is just going to be IB RTH plus VBE plus, instead of IE, we just write IB, beta plus 1, all right, and times RE, all right. So then collecting IB together, all right, so you're going to get VTH is equal to IB bracket RTH plus beta plus 1 times RE, and then all of that you add with VBE. All right, so now we can write an expression for IB. All right, so IB is going to equal to VTH minus VBE, all divided by this term here. All right, so it's all going to be, oops, where did we go? So all that is going to be divided by this part here. All right. All right. So let's just work this out. So VTH is 2.25. 2.25 minus 0.7. That's volts divided by RTH, which is 7 kilo ohm. RE is, okay, so 7 kilo ohm plus beta, which is 150 plus 1 times RE, which is 680. All right. This is in kilo. Sorry, this is in ohm. Oops. All right. So that's going to be equal to 2. Let me see. Was that 14.13 microamps? All right. So that's our IB. So now that we know what IB is, so therefore we can work out what IC is. All right, so work out what IC is. So IC is therefore, IC is just beta IB. All right. So that's just 150 times 14.13 microamps. So that's going to be equal to 2.12 milliamps. All right. All right. So the rest is, well, that's the answer for IC. Now to work out what VCE is, if you look at the circuit here, VCE, or here, it doesn't matter whichever way, right? Whichever one. So VCE here is just simply V1, which is the whole thing from top to bottom, minus the voltage across here and minus the voltage across here, RE, right? So we can work out what IE is, all right, from the transistor current equation. So IE is just simply IC plus IB. All right, so that's just going to be 2.12 milliamps plus 14.13 microamps. All right, so just be 2.12 plus 14.13, so it's 2.13 milliamps. All right. All right, so then we can work out the rest. So let's do VRC first of all. So VRC is equal to IC times RC. Sorry, I need to do it again. VRC is equal to IC times RC. All right. So that's 2.12 milliamps times RC, which is 2.2 kilo ohm. So that's going to be 2.12 milli times, sorry, 2.12, yeah, 2.12 and 2.2 times 2.2 kilo, so that's going to be 4.66. So that's 4.66 volts. All right. And similarly for VRE, that's going to be equal to IE times RE. So IE is 2.13 milliamps multiplied by 680 ohms. So that's going to be equal to 2.13 milli times 680. So that's 1.45. So it's going to be 1.45 volts. All right. So now that we have everything, basically, again, the maybe I'll just write down here right loop equation. All right, is just equals to that's this side here, right? This side here. All right, so I can write V1 is equal to VRC plus VCE plus VRE. Right? Okay. So we can straight away work out the value of VCE. All right. So VCE is equal to V1 minus VRC and minus VRE. All right, which is going to be equal to 18 minus 4.66, and then minus 1.45 volts. So that's 18, 4.66. So that's 18 minus 4.66 minus 1.45. It's going to be 11.89. So it's 11.89 volts. All right. So that's the final answer. All right. Hopefully you guys understand. I mean, the only extra complexity here is the fact that we have to convert the left side of the biasing, the base biasing, into a Thevenin equivalent. But once we've done that, the usual way of analyzing our transistor bias circuit is as per before. All right, so until the next video.